A quantum computer doesn't look or act at all like the computers that we use every day. It relies on different laws of physics to run calculations at super fast speeds.
What happens when a computer stops waiting for time? Google just ran a quantum core that finished in minutes what ordinary machines would chase for longer than the universe has existed. That means answers can now arrive before the question is even done. A result from the far future suddenly lives in the present. If that is real, every system built on slow math is exposed, and whoever controls this kind of speed controls discovery. 5 minutes versus forever. Google's team chose a problem that punishes regular computers. It was not a business spreadsheet or a video render. It was a wall of random quantum circuits that grows in complexity every time you add another qubit or another layer. A classical machine has to trace each path like a person listing every possible chess game. Even the fastest supercomputers would need longer than the age of the universe to finish that list because classical systems move in sequence. One calculation, then the next, then the next. Google's new quantum core did something different. It let the system hold many paths at once, measure them as a single picture, and collapse the result in 5 minutes. 5 minutes against a number of years so large it stops feeling real. That is why people said it destroyed linear time. The computer did not cheat. It just refused to walk through time the way we do. Engineers will argue that this was a laboratory task and not a real-world application. That is true today. It will not stay true. Every major quantum milestone starts with a narrow test and spreads into fields that said they were not ready. The same playbook happened with machine learning. First narrow, then general, then everywhere. What matters is not that Google ran this specific benchmark. What matters is that it proved a machine on a lab bench can deliver answers at a pace that makes human planning look slow. Once you can do that with one problem, you can start to map other problems onto the same hardware. Chemistry, logistics, weather, energy, finance. Anything that explodes in complexity when you add more variables is now a target. Once a machine shows it can ignore the usual limits, other machines will follow because every nation will want the same leverage. A 5-minute answer to a forever problem is not a curiosity. It is a strategic asset. Whoever owns the box that bends time controls how fast others can react. So we have to ask right now. If one company can already do this in a protected lab, how long before a government demands exclusive access, and what happens to everyone else when the clock for innovation is no longer a decade but a day? Another consequence hides in plain sight. When results arrive this quickly, legacy review cycles collapse. Peer review, board approvals, safety gates, procurement calendars, all of them were built for discoveries that took months or years. A discovery that takes minutes makes slow oversight look like neglect. That pressure will push institutions to shorten their own timelines, which increases the chance of mistakes, which in turn makes the fastest actor even more powerful because it can correct faster than anyone else. That is why this moment matters. What does time-free computing actually change first today for us? When time becomes a loop. The most unsettling part of Google's announcement was not the raw speed. It was the hint that the core could hold states in repeating cycles without losing precision. Classical systems always pay for time. Clocks drift, memory cells leak charge, batteries fade, bearings wear. Quantum systems built around stable phases and error-corrected qubits can do something closer to the opposite. They can enter patterns that repeat without aging. Physicists call some of these phases time crystals, systems that tick forever under a steady drive. In practice, this means a computer can keep data or a calculation path alive for as long as you keep the lab stable. No more periodic refresh. No more bit rot. No more fear that a long simulation will degrade before it finishes. For industries that run round-the-clock logistics, radar networks, satellite swarms, this is not a curiosity. It is an answer to a problem that has cost billions of dollars in maintenance. Once you have loops that do not decay, you can build services that never need a reboot. Navigation constellations could hold their calibration for decades. Power grids could run forecasting cycles that refresh every minute without drifting away from reality. Climate labs could keep digital twins of the atmosphere always running and always synchronized. The machine does not have to start over because for it there is no over. That kind of stability changes how software is written. Today we write code to survive failure. Tomorrow we will write code to stay in a clean rhythm. The hard part will not be the math. It will be keeping the physical environment quiet enough for the loops to stay pure. But this hides a sharper twist. Cycles that do not age are perfect training grounds for artificial intelligence. An AI that can run in a time loop can test, evaluate, and correct without the usual pause for hardware resets. It can iterate through thousands of policy choices while the human team is still drafting a strategy memo. It can probe failure modes in medicine, finance, even air traffic control, and surface the safest option before the people in charge have even gathered for the meeting. That is power because it lets whoever owns the quantum loop move from forecasting to pre-deciding. It makes slow rivals look reckless because their answers arrive when the risk has already passed. And if loops can run in secure facilities, they become invisible engines of advantage. So the question at the end of this loop is not can we build it? The question is who gets to keep a machine that does not get tired. How do we audit a decision born in an environment with no clock, and what happens to trust when systems begin to act before anyone asks them to explain why? The next leap is even stranger because it does not only bend time inside the chip. It bends cause and effect itself. But if discovery no longer waits on time, can our networks, power grids, and AIS react fast enough to use answers that arrive instantly? Out of order on purpose. Classical computing is built on a simple rule. First do step A, then do step B, then decide what to do next. Quantum devices are starting to prove that this order is not always necessary. In some experiments, two operations can influence each other without a fixed sequence. Event A both comes before and after event B. The final answer is what decides which path mattered more. This is called indefinite causal order, and it sounds abstract until you map it onto real systems. Picture a global delivery network that can test every route both directions at once and then pick the order that delivered the best outcome. Picture a power grid that can look at yesterday and tomorrow at the same time and route energy in the way that prevents overload. Picture financial exchanges that can resolve trades in the sequence that keeps the market most stable instead of the sequence in which the orders arrived. That is not a faster calculator. That is a planner that reaches across time to choose the version of events that causes the least damage. This breaks more than scheduling. It breaks the way we build trust. Today we can audit a process by rewinding the log. We say this happened first, then this, so here is the path to the decision. In a system with indefinite order, the path is shaped by the outcome, not the other way around. You can still log the physics and you can still record the inputs, but the explanation to a human becomes harder because our language expects before and after. Regulators, insurers, and courts will have to decide whether they will accept decisions that do not have one clean timeline. Many will say no at first. Yet the advantages will be hard to ignore. Networks that can reorder events dynamically will waste less energy, lose fewer packets, and stabilize faster after an attack. Security tools that can test multiple response sequences at once will stop intrusions before the attacker finishes the move. Air traffic systems could check landing orders and takeoff windows in parallel and then pick the blend that moves the most planes with the least fuel. Once one nation or one tech giant adopts systems that rewrite order on the fly, everyone else will follow even if the explanation is messy, because nobody wants to be the only player waiting on linear cause and effect. The next chapter looks at what that race does to encryption, to money, and to every field that hides behind slow math. To live with this kind of machine, we will need quantum audit trails that tag every branch, plus human timeouts where people can pause an automated choice before it locks. Those controls will slow the system a little, but without them nobody will trust outcomes that arrived faster than the question that triggered them in the first place. And if quantum systems can bend order itself, what does that do to trust when the path to the answer is no longer in a straight line?